Good morning, everyone. It's Thanksgiving 2021. And before I start today's segment about intake ports, let me give thanks to our servicemen in the U.S. Marines, which I know one very, very close to me, my stepson, Alex Santos, and another one from the Albuquerque area is Sergeant Corey Gonya, and of course Isaac Gibson, my buddy at LAPD, and another one, Steve Algori, an ex-pilot for the U.S. Marines, and he recently retired from the airlines. Anyway, that's just a little shout out to my my stepson and the other Marine Corps friends of ours in the family. Anyway, today we're going to talk about the intake port. Here's what we have. Okay, is an illustration of the standard 20 degree, that's about a 20 degree, 23 degree small block Chevy and Ford port angle. There's the deck of the block, same thing here. And this is like a Yates SB2, more of the new style cylinder heads. Anyway, there's a very big difference in power here between these two, and I've said in other previous articles on Facebook that I wrote about. I had a small cylinder head that was a Yates back in the early 90s, late 80s, if I remember correctly. I made about 800 horsepower, 283 CFM. That's telling you it's just not about flow. It's got a lot to do with the swirl and tumble situation that's present with the new high port heads. But here, there's a lot of swirl, okay, and of course tumble, plus the port bias going to the left or the right. But the more you straighten it out, there's less and less swirl and more of a tumble situation on the heads. But we'll talk about that in a little while. Anyway, what we're looking at here is the intake port, and I talk more about the intake port more than I do the exhaust, due to the fact that the intake port has to keep everything in suspension, keep the mixture together with the air, keep them suspended and mixed up pretty good so that when they discharge into the combustion chamber, you have basically a good homogeneous quality that's very it will have an effective burn rate, as opposed to like a lazy port where you have a lot of rich and lean situation inside the combustion chamber, a lean here, rich here. There's uneven combustion going on. But here we go. The chambers on the old generation heads, they start with 64 to 74 cc's. And on this new late style cylinder heads, they're about 35 to 45 cc. What does that mean? This port basically was tilted this way, okay? It's kicked up, and when it's kicked up, this area closes up. So this becomes a more smaller chamber as opposed to this open chamber here. It closed up this way. Now, with that being said, the spark plug location actually goes higher. So now what you've done when you rolled the heads this way, you don't have a dome on top of the piston. The spark plug's over here. It doesn't have to go over the dome. You can actually run a higher compression with a flat top. Now, with a 91 compression ratio on a 63 cc, that's a typical Ford HO. 9-to-1 compression ratio, 63 cc. Now, when you take that and put a 40 cc cylinder head, granted that you have the valve clearance, guess what happens? It becomes 13.6. That's a gain of compression, okay? Taking into account 30 to 40 cc, to 40 horsepower per compression point, you're looking at probably 150 horsepower just swapping the heads over. You're creating a better burn rate with a flat top, so you don't need that dome, that intrusive dome, because with the big dome right here, once you create the spark, it's actually lower here. It has to go over the dome. Not only is the piston heavy, but the dome, it looks impressive. Everybody's impressed by the dome, but actually splits the combustion chamber in half, especially when that thing is really deep into the combustion chamber. They go, oh, that looks radical. That looks great. Actually, it splits the combustion chamber, which is not good. Now, here we are with the new configuration. So you just gain 150 horsepower due to the combustion chamber shape, but the compact chambers, as opposed to the big chamber, it contains the heat in a smaller area, okay? And then when you have a smaller area, you're not dissipating as much. Remember, heat is energy. Heat is power. If the ignition front is dispersed in a wider area, you have so much more surface that's taken away, that heat energy. Instead of pushing the piston down, it takes it to the water jacket. Bad situation. So, compact chamber, more efficient combustion. High spark plug application, we talk about that. Now, the ignition lead time or total is about 26 to 30 degrees. I've experienced this back in the late 80s, and I was going, okay, this is telling me something. Okay, the old heads that we used to run, after you milled it, it still required 36, 38, as high as 44 degrees on some of the small block Chevrolets. And that's horrible. When you're looking at, 8 degrees less ignition lead time, that means on the old combustion chamber, you're sparking it right here, okay? But if you have 8 degrees less distance while that gas is expanding, the piston doesn't have to fight that going up. Now, if you're sparking towards much closer to the top TDC, there's less negative torque that the engine has to overwhelm in order for it to get to TDC, and then the flame front to finally get completed about 18 degrees. Okay, 15, 18 degrees, depends, somewhere out there. Then you have an effective combustion chamber, and it'll give you horsepower, big time horsepower. Now, with this, well, let me get back with that. I've done an article on Facebook that's been shared all over about the difference between airflow on a flow bench and airflow on a running engine. What happens on a flow bench is that it's always stated, the short side is important. I agree. The short side is important according to the flow bench, especially on a kinked up port like this. This is very important. True, but in the real world, it's not flowing continuous in a laminar characteristics. What it has is this, okay? It's going like this. The stop and go, the valve opening, it'll accelerate, it's shut, it'll stop, okay? And when it's going like this, okay, at a very fast pace, what actually happens is that the port, when the valve closes, all this flow comes in, it stops on top of that valve and they stack up. All right, that's what you call port recovery. The faster they stack up, the port recovers, meaning the next valve opening, it shoves it in there. Especially when the column, the pressure waves are going like this, okay? It hits and it starts stacking up, bounces back, comes back until, let's just take, for example, it's up here, okay? When it's at that distance, the moment the valve opens up, the intake valve opens up, and the column again, the pressure wave comes in and piles up on top of that again, there's an artificial supercharging effect through the valve. All the column comes in and stack up and force it in. Now, that being the scenario, the short side comes into play because the pressure wave is over here, okay? And then it'll see this action here and it'll hug that port and discharge in the combustion chamber. Very important. But at maximum lift, when the port is finally depleted, you'll see the straight line happening. When you look at the sheet metal intake, you notice the port doesn't come in this way. it comes in pretty high angle. Same thing here, pretty high angle. But there's less turn here as opposed to here. It's a little bit more, because the flow really at high RPM wants to do this. It wants to travel in a straight line. Okay? It completely bypasses this guy here. Now, when you have a race port, sometimes there are negative things happening. With a port speed going on here, this is bypassed. And a lot of you head porters out there, there's a lot of you guys are way, way better than me. I know that from experience. Take a screwdriver like this. Let's say you're a 750, 800 lift or 900 lift. Stick a screwdriver there and watch your flow bench numbers. Okay? And then go like this here. Stick it and tell me what your flow bench sees. I bet you're gonna see something really nice. Something to think about. So you stick that. What you actually did was you made a vortex generator. Okay, it sees an intrusion here, and the air kind of sticks to it and manages to take the short side. You have some activity. Now, I did some work on some cylinder heads back east. Sometimes when you do that, you actually have that decrease in flow. On that motorcycle head, we had 10 CFM less flow, but we had 20% more power. 23% to be exact. Think about that. Again, it's not about flow. You're getting some activity here, and you're dispensing the fuel more evenly. Instead of having a rich, lean, you're having a little bit more here, okay? It's more of a dispersal issue, creating a better burn pattern. So put that in mind. Here's another situation that I've been doing. When your buddy or customer finally says, Ben, I need more power, or Jim, I need more power, I cannot afford the next step up on cylinder heads because now I got to change rocker arms, everything's changed again. And what I've been doing is this. I've been putting a plate right about here. Okay? I add a plate. An aluminum plate. Sometimes I stack two of them. But what we have is this. Some heads out there, TFS, you can race them, oh my God, half an inch. That's quite a bit. Or some are average 400, a little below half an inch. Here's what happens. Oh, excuse me. Now you see what the port angle does? There's your port angle. It changes drastically. Now the short side becomes less of an issue. There's not much pressure for this to function correctly as opposed to this one. Now, with a port plate, and I'll post pictures right after this video. It's kicked up, it's kicked outward, so you can still use the same manifold. All you got to do is do some modifications on the carburetor because it's lower. Sometimes hits the bottom of the manifold. But what I found out with this port race half an inch, I'm not gonna say which cylinder heads you could do that. You know, I can't give everything. I'm getting 35 CFM. Okay, it basically, the little length, oh, and here, if the guy's got a little bit of money, you can weld it. But what I've done is I use A and B 2-part epoxy. and then I kind of roughen up the floor so that epoxy has something to stick. And 35 CFM is what I see. When you start manipulating this, to a certain extent, you can get about 40. That is big. Remember, what you want here, this is like a velocity stack. If you visualize this, you want that kind of a velocity stack effect on the valve. The same thing here. Because if you would have just intersected straight out with no short side, you're going to have half a stack and you're going to blow the cone to bring in the flow. 35 CFM, how big is that? Okay, that's about 80 horsepower on a really impressive cylinder head. Let me use, for example, the AFR 220 and versus the AFR 205 on the Fords. 338 on the 220, 331 on the 205. That is with a bigger intake valve on the 220. It's a 15 cc difference, and the net gain is 7 CFM. These are not my numbers. These are AFR's numbers. 7 CFM. Think about that. 35 CFM. Okay? If we're getting 10 CFM, it's 20 horsepower. This is below 10. So let's say you got 15. How much are you getting out of that? 7 CFM, 35 CFM. Now, on a TFS Chevrolet standard Chevy, not the LS, the 215 flows 287 at 700. The 230cc runners flow 310 at 700. That's 23 CFM. It is less than half of what this is capable. And like I said, when you start playing with this, okay, and start sticking the screwdriver there, and I don't want to say directly what you want to find out or how you're going to do this, but this will give you an idea. When you stick a screwdriver there, you're going to pick up flow. When you stick a screwdriver here as well, some of these old school heads also picks up flow. Okay, now, the faster the airspeed, okay, here we have swirl, tumble, whatever. If you have a port bias and then a little bit of a, what they call port shrouding, it creates a swirl and a tumble, okay? Here's you got a tumble and you also have a swirl. It is important that when you start modifying ports, you take those into account, especially if you have a road racer or a short track, you know, half a mile oval track, something that like a Willow Springs, a big track, you need that throttle response, which swirl and tumble gives you. But now, the higher the RPM, swirl and tumble takes a lesser role due to the fact that when you have this motion, swirl, and this tumble, and then you smack it with compression, boom, okay? It will ignite. You have perfect combustion characteristics. But the faster you go, sometimes when it's taking a longer distance, okay, so doing this, it's a detriment to power, because now what people have to realize, at high RPM, there's so much intake and closing going on. It's going like this. Okay? You know what that does? By itself, swirl and tumble is its own mixture motion. Okay? But when you have high RPM going at a rapid rate, opening, closing, it's shaking that whole air and fuel already in here. It's creating its own mixture motion from the RPMs. Then when it gets in here, it's dispersed. It's a bit shook up quite a bit. The higher the RPM, the more that's going on, going like this. And sure enough, tumble and swirl plays a lesser role at high RPM. That's why when you see people go, I want maximum flow. Yes. Don't forget about swirl and chamber. Also yes. But RPM has an effective mixture motion because of the rapid cycling going on here. So by the time it gets in there, you have good combustion characteristics. Okay, now that's the effect of faster airspeed. The only problem with higher ports as opposed to the low ports, the port length becomes longer. Okay, so consequently, sometimes you pay some kind. Remember, you don't get anything for free. When the manifold stays up, this stands up, it's a longer runner. Correct? So I don't think you would just raise the port and leave the floor where it's at. Now you have too much of a difference of the short side and the long side. Ooh, not good. If you can keep, like they say, when you can keep that port consistent, all right? The best port in the world is a round port that dumps into a center valve like this, and then a round port. But once you start bending it, okay, it has unequal sides, low and top side. And when you get to this point, it has to open up, expand in order for it to slow down and negotiate the turn. And so if there's some activity there, okay, so it starts to open up here so it can take the turn. Now, what else do I have here for my notes? Now, intake and exhaust, porting, boost situation. Now, let me say something. I've worked on quite a few boosted heads for the Hemi, these Hellcats. When you look at the Hellcat head, the flange is this way. The Hellcat cylinder heads, it's got a, oh man, I'm messing up my drawing. The flange is like this. Okay? When you put it on the flow bench, this two unequal side will screw you up. What you need to do is take a little adapter and kick it out to here. Okay? So, because on the top side of the Hellcat and other supercharged heads, it's too short. When you have your clay or your radius entry comes in, it kind of like shakes it up a little bit. It doesn't get any stability. And this one here, it's got stable flow. So you get this uneven pulling and your reading is going to be false. That said, you put that extension, make it out of plastic, or you can fashion it out of epoxy, put it on and watch your reading. It's going to change. But here you are porting an engine that's boosted. Flow bench runs on vacuum. The only time the cylinder head sees vacuum is when it's idling. Do you know anybody racing at idle speed? So what I do, I set my machine to run exhaust, basically blowing into the intake port, mimicking a boosted situation. Why are you evaluating a port under vacuum? I don't know. When it's the only time it sees vacuum is at idle. You guys follow me? So, evaluate this like you're boosting the heads. Because that sucker will not see vacuum only when it's idling. Everything is a boost. So you pressurize it, put this angle plate, pressurize it, and get your reading and look at it. You can change your valve angles, all that stuff. Same thing with the Coyote. The Coyote heads are like this, even taller, with a flat flange right here, right? And then it comes in this way. Look at what you have. There's the flange here. Hopefully fix that and then boost it and see what you have. Okay, I I think that's something for everybody to think about. And I would like people, give me questions or whatever. I like questions because it makes me think. Sometimes you have the same thing on there, and when you see somebody coming in from a different angle and telling you something, you go, okay, I'm following where this guy's coming from. Okay, he's pretty sharp too. Like I said, this is not a one-way street. I learn from you guys too, from the questions, and we all learn together. Hopefully, get these things more of our exercise or our quest for speed and power, plus efficiency, is helped by having discussions such as these. Anyway, please subscribe to Ben Alameda Racing so I can keep this going. And again, I might do another intake port segment. Then I'll switch to combustion chamber. Like I said, I keep coming back to the intake ports because you could screw this up big time and ruin the function of the port by having fuel air separation, no velocity, okay, fuel drop off, exhaust spent. Once you created combustion, you get so much pressure, temperature, and everything, that exhaust opens up, boom, out it goes. Kind of hard to screw up. Well, talking about screw up before I close. The Boss 302 and the Boss 351, especially the Boss 302, small cubic inch, gigantic intake port, okay, with a 224 for 1969 valve and a 219 on the intake in 70. Oh my God. You don't port them to gain more power. You actually epoxy them to gain velocity without losing port signal and all that, without losing velocity. The exhaust is kinked up really bad. But you know what? If you dyno a Boss 302 stock against a Z28 302 stock, even with a kinked up exhaust and an overly big intake port, it still made more power. Okay? There's somebody out there that did that, two stock ones. Oh, also, this new cylinder heads, rectangular port, squared off on the corner. The newer ones are rounded off the corner, right about here. Okay? Your dead zones are small, so more of the flow comes in. Here, the dead zones are big. All right? By the time you look at this and visualize the dead zone, it starts to look like this. Okay? The rounded corners will minimize the dead zones in the port. And then when your valve center line is over here, you'll see the flow column tend to bias towards there. If your valve center line is here, you'll also see your flow column majority is over here. Only that you'll see that when the valve center line is straight to the port, but in a two valve arrangement, you're always going to have a port bias to one side, and that's where your activity. And last thing, there's so much to talk about. You don't port to bring the air to go where you want it to go. It's going to go where it wants to go. All you can do is realize where it's going. Is it effectively towards the lower left, okay, or middle left, and help it there. Okay, you're not going to change its mind. It's going to go where it wants to go. No magic will say, oh, I'm going to bend this port this way so the flow will go this way to the right. No, when the flow is going predominantly strong to the left and you extend the one on the right and thinking that it's going to go that way, it's not. It never will. It's going to go where it wants to go. Okay? So this is it. I hope I didn't forget anything. Look at my notes. Thanks, guys. All right, so I'll come up with another one, hopefully soon, and we'll follow up. Okay? Thank you. Hey, have a nice Thanksgiving, guys, and be safe out there. Okay? Take care. Bye-bye.